In this review problem, we're going to take a look at how to solve this differential equation using the technique of Laplace transforms. So we'll start off with y double prime plus 4y prime plus 4y equals e to the minus 2t, taking the Laplace transform on both sides. The Laplace transform of y double prime is s squared times y of s minus sy of 0 minus y prime of 0. The Laplace transform of 4y prime is 4s times y of s minus 4y of 0. And then the Laplace transform of y is just simply going to be 4 times y of s. Then using our table of transformations, the Laplace transform of e to the minus 2t is 1 over s plus 2. Okay, now let's get all the y of s's together. We have s squared plus 4s plus 4 times y of s. So that's these three terms. Then minus s y of 0, that's 4, so minus 4s. Minus y prime of 0, that's 3. Then minus 4 times y of 0, that's 4 times 4, or 16. And that's equal to 1 over s plus 2. So that gives us that s plus 2 quantity squared times y of s is equal to 4s plus 19 plus 1 over s plus 2. So that y of s is equal to 4s plus 19 over s plus 2 squared plus 1 over s plus 2 to the third after dividing by s plus 2 squared. Okay, now there's so this reduces the differential equation to an algebra problem. The trick is going to be finding the inverse transform of this. To do this, we'll use partial fractions. There's about 3 different ways this can be done, and I'll do them just to give an idea of how this can be accomplished. So method number 1, let's write y of s as something all over s plus 2 to the third. So that's going to be 4s plus 19 times s plus 2 plus 1. So multiplying out, we get 4s squared. Then we have 19 plus 8 makes 27s. Then we have 38 plus 1 for 39 over s plus 2 to the third. Okay, from this point forward, it's a matter of identifying the expansion. So 4s squared minus 27s plus 39 over s plus 2 to the third. And this is supposed to be equal to a over s plus 2 plus b over s plus 2 squared plus c over s plus 2 to the third. So clearing out, we get 4s squared plus 27s plus 39 is equal to a times s plus 2 squared plus b times s plus 2 plus c. Okay, from this point, we can match coefficients. Alternatively, at least to get started, we can plug in s equals negative 2 to see what happens. If I plug in negative 2 on the left-hand side, I get 16 minus 54 plus 39. If I plug in negative 2 on the right-hand side, I just get c all by itself. So c is equal to 55 minus 54, so c is equal to 1. Now, to solve for a and b, there's 2 ways of doing it. We could multiply out the right-hand side and match coefficients. That works. Another technique, not necessarily better, is to plug in 2 other numbers. Let's plug in 0. On the left side, I get 39. If I plug in 0 into the right-hand side, I'll get 4a plus 2b plus c, which I already know is equal to 1. Let's plug in something else that's convenient. Let's plug in negative 1. If I plug in negative 1, then both of these are equal to 1. And I get a plus b plus c. And if I plug in 1 or negative 1 on the left-hand side, I'll get 4 minus 27 plus 39. 39 minus 27 is 12, plus 4 gives me 16. And so I get a system of 2 equations and 2 unknowns. And if we solve this system, this will provide that a is equal to 4 and b is equal to 11. And so there's my a, b, and c. Okay, so that's the first method by which we can solve for the a, the b, and the c. As I said, this is a little bit more work than it had to be. Let's talk about a second method. Method number 2. Let's see. So this is y of s is equal to, so we have this part here already has the right form. This part here is going to go a over s plus 2, and then b over s plus 2 squared. So there's no need to worry about this part here because that already has the right form. In other words, when I did all this work here, I found that c was equal to 1. Well, I could have figured that out right off the bat because I had this already. C was equal to 1. 1 over s plus 2 cubed was already an expansion. So let's just worry about this part all by itself, and then whatever I get, I'll just add this on separately. So let's write this as equal to 4s plus 19 over s plus 2 squared all by itself. And then whatever I get for this, I'll just add this on separately. Multiplying, we get a times s plus 2 plus b is equal to 4s plus 19. If I plug in s is equal to negative 2, that means that b is equal to negative 8 plus 19 is 11. And if I plug in something else, let's say 0, I get that 2a plus b is equal to 19. So that 2a plus 11 is 19. So that a is equal to 4. And I get the same answer that I had before. So that means that 4s plus 19 over s plus 2 squared is equal to 4 over s plus 2 plus 11 over s plus 2 squared. And so if I add on that extra s plus 2 to the third, I'll just add on the extra 1 over s plus 2 to the third on both sides. And so there's my expansion. So that's the second method. Third method. So it was 4s plus 19 over s plus 2 squared plus 1 over s plus 2 to the third. Another way this can be done is as follows. Let's write this as 4 times s plus 2, like that. Then I have plus 19, and obviously I need a minus 8 to compensate. 4 times 2 is 8. Over s plus 2 squared plus 1 over s plus 2 to the third. So that's equal to 4 times s plus 2 over s plus 2 squared plus 11 over s plus 2 squared plus 1 over s plus 2 to the third. And then this last fraction, s plus 2, cancels one of the s plus 2's in the bottom. I get 4 over s plus 2 plus 11 over s plus 2 squared plus 1 over s plus 2 to the third. So the point that I wanted to make with this 3 different methods is that there's several ways that the partial fraction decomposition for capital Y of s could be found. Okay, so coming back to the original problem here. So we found that y of s was equal to 4s plus 19 over s plus 2 squared plus 1 plus s plus 2 to the third. And the partial fraction expansion is going to be 4 over s plus 2 plus 11 over s plus 2 squared plus 1 over s plus 2 to the third. Okay, from this point forward, we have to use our table to figure out how to find the original function. So y of t equals, referring to the table, make the papers a little flat here. Okay, the first bit comes off this part of the table, 1 over s minus a. That fits this pattern, so I get 4 times e to the minus 2t. The next part comes further down. here I have 11 times 1 over s plus 2 squared. 1 is equal to 1 factorial. I have a 1 plus 1 as the exponent. So my rule is going to be 11 times t e to the minus 2t, using the negative 2, the minus negative 2 down here. This last part I got to be a little bit more careful about. Here I have a 2 plus 1 as the exponent. So I need a 2 factorial in the numerator, which means I need to multiply by 1/2 to compensate. So this part right here, the inverse Laplace transform is going to be t squared e to the minus 2t. But I also need this extra 1/2 to compensate. So this half comes from the fact that there's a 2 factorial in this numerator to apply this rule for the inverse transformation. And so using Laplace transforms, that is the solution of the differential equation.